So let's consider what would happen if something was placed underwater. So we have a container right here of water, or some other kind of fluid, doesn't have to be water. And we have an object in here, and this object is sitting underwater. Now, to make the math easy, we're going to say like a rectangular or cylindrical or something object that's symmetric. So what's going to happen is there's going to be pressure pushing on all these sides, but look at the top and the bottom. The bottom is going to have a different pressure than the top because it's deeper in the water. And so what we have is, let's say the distance to the top is going to be some h1, distance to the bottom is going to be some h2. So the pressure at the top, so pressure 1 is going to be equal to rho g h1. The pressure at the bottom is going to be rho g h2. Okay. Now, free body diagram for this object, we got mg pushing down. There's the pressure on the bottom exerts a force F2 up. The pressure on the top exerts a force F1 down. Okay, and so that means that what is F2 or F1? F2 is going to be P2 times the area. F1 is going to be P1 times the area. So we know that F2 is going to be greater than F1. So the difference, delta F, is going to be P2A minus P1A. Okay, so the delta F is going to be P2, which is rho G H2 times A, minus rho G H1 times A. Okay. Well, that's going to be rho G A times H2 minus H1. But H2 minus H1 is the height of the object. Height times area is volume. Volume times rho is mass. So the delta F is going to be equal to mg. Now, wait a minute. This m is not the same as that m, because this rho is the density of the fluid. So this mass is the mass of water times g. This mass up here is the mass of the object times g. So what happens is that we've got mg down, but there's a net upward force mass of water times g. So this is actually the weight of the displaced water. So we call that the buoyant force. So the buoyant force is equal to the weight of the displaced water. Okay, so that means, okay, so let us do an example problem. Let's say that we've got a block 4 centimeters, 4 centimeters, 4 centimeters of aluminum. Okay, and I want to know, what does it weigh? Well, we know that the density of aluminum is 2,700 kilograms per meter cubed. That's the same as 2.7 grams per cubic centimeter. So the volume is going to be 4 centimeters cubed, which is 64 cubic centimeters. So that means the mass of the aluminum is going to be 176 grams, so that's 0.173 kilograms. So the weight is mg. So that means that mg is going to be 1.7 newtons. Okay, so that's in air. It is underwater. So I have the same block, and it's submerged in a container of water. So now we know that we got mg pulling down, and we've got a buoyancy force upwards. So what's the buoyancy force? So the buoyancy force is going to be equal to the mass of displaced water times g. Well, what's the displaced water? Displaced water is going to be the density of water times the volume of the object. Well, what's the density of water? That's 1,000 kilograms per cubic meter, or 1 gram per cubic centimeter. So the mass of the displaced water would be equal to 64 grams, or 0.064 kilograms. So the buoyant force would be equal to 0.63 newtons. So that'd be 0.064 kilograms times 9.81 meters per second squared. Now the question is, if this thing is hanging underwater with a rope. Now, if it is just hanging in air like this, what's the tension? Well, we got tension up, we got mg down, so the tension equals mg, and so the tension would be 1.7 newtons. That's in air. But what if it's underwater? Okay, well now, free body diagram, we would have the block here. We've got mg pulling down, okay? We've got buoyancy force up, and we got tension up. So it's clear to see that tension plus the buoyant force equals mg. So the tension is going to be equal to mg minus the buoyant force. So that's going to be equal to 1.7 newtons minus 0.63 newtons. So the tension is 1.07 newtons. Now notice the tension is 1.7 newtons if it's in air. It's 1.07 newtons if it's underwater. Okay, so what does if you had an object right here of some mass m prime and some tension, if the tension is 1.07 newtons, that tension has to balance m prime g, so m prime would be t over g. That would be equal to 0.109 kilograms, or 109 grams. So what that means is, if this thing is hanging underwater here, that tension that's holding this object, and we know the object is 173 grams, the tension is the same as the tension holding a 109 gram object in air. So it feels lighter underwater because you have the buoyant force pushing upwards. So 109 divided by 173 is 0.63. So that means it weighs 63% of what it would in air when it's underwater. Okay, so that's an example of the buoyant force. Now, what would happen to something like a block of wood? Now, some different wood has different buoyancy, but let's consider a block of wood that has a density of maybe 0.75 grams per cubic centimeter. Well, what would happen is, because the density is less than the density of water, that would mean the same volume of wood weighs less than water, so the mg of the wood is going to be less than the equivalent weight of displaced water. So that means the buoyant force will be bigger than mg, and that's going to push it upwards, and it's actually going to push it upwards until it's floating partially out of the water. So the amount underwater displaces the weight of the water. Well, given that, you would say that 75% of it would be underwater and 25% would be above water. And so again, this is buoyancy in action. The idea here, buoyancy, is basically the idea of how submarines work. and that is that you have chambers in here that you can flood with water that increases the density of the submarine. So if the density of the submarine equals the density of water, then it's neutral. It stays at a certain depth if it's underwater. Okay. If the density of the submarine is greater than density of water, then it descends. Okay, if the density of submarine is less than density of water, then it ascends. And so basically, you take air and force the water out. That decreases the density, and then you can surface. You flood those tanks, and then you can submerge. Okay, and if you keep it neutral so that they're partially flooded, then what can happen is the submarine would stay at whatever depth it is. And so this is all related to buoyancy.